kind of maybe. So today we want to welcome a couple people, but before we do, I want to thank a couple people. One isn't here. Is Christina here? So I always like to, when I can, explain how these things come about. I was talking to Christina. She's a class member here in the office one day, and she talked about taking former students or students she has now, I'm not sure, to the planetarium. And I said, planetarium, what's that? So she told me about it, and I Googled it and tried to contact them without any luck, unfortunately. I guess they're busy people. And then I want to thank Ramona here, because we had a speaker here one time, and she asked the speaker a question, and I thought, oh, that relates to the planetarium. Maybe she knows something. So I went over to her and I said, I've been trying to get a hold of them. She goes on her phone, blah, 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 and then we had the connection right then and there. So thanks to Christina and Ramona for helping us with this. We have two speakers today. The way it's going to go first is that Lisa Goodman, who I'll introduce first, is going to do a short presentation on the planetarium, and then we'll have a Q&A a little earlier than usual. And then Dr. Kerr will do his presentation, and then right before the break, we'll do a Q&A, and then he'll continue after the break, and we'll have another Q&A. Dr. Andrew Kerr is the manager at the Dale Etheridge Planetarium at the College of Southern Nevada, CSN, which is not at CSN, which I'm sure they'll explain. It's at a different location. He received his PhD in astrophysics from the University of Missouri and went into teaching at a small college in Ohio. He says on his bio, he inherited the planetarium there, and it rapidly became the best part of his day. He came to Las Vegas in 2014 to be only the second manager in the history of the planetarium at CSN. Lisa Goodman is the Educational Programs Coordinator at Dale Etheridge Planetarium at the College of Southern Nevada. She's originally from Coney Island, New York. Wow. All you New Yorkers, raise your hand, please, that are here. She has been passionate about the universe and humanity's place in it ever since she was a little girl. Forever loves learning about theoretical physics, the solar system, and astrobiology, especially Saturn's moon, Titan. As an informal educator with a background in education and physical sciences from the City University of New York. Anybody go to City University? No. Oh, right there. Okay.
I know what it is.
She tries to inspire the next generation of space scientists and explorers through her work at the planetarium and with community outreach. So let's give an initial hand to Lisa Goodman.
Our volunteers called our Ambassadors of Astronomy, and two of them are here with us today. Ramona and her sister Nancy help us out throughout the year, and we're very grateful for that.
We're going to talk about NASA's great observatories and beyond a little bit. So you've got the original four here listed, and that is Hubble, Spitzer, Compton, and Chandra, and we'll get into each one of them. But then this was the great observatories from the 90s. This was what they referred to them as. And then as we have gone on, we have added more observatories that are just as great, but these were the beginning, and so they've basically retained this designation of NASA's great observatories. So we're going to start off with an image, and I wish I could have made it bigger. You can find all of these images online. But so this has from Spitzer, from Hubble, and from Chandra, which are three of the four. And you might be asking them, well, what about Compton? Why don't we have a picture for it up here? Compton was gamma ray observatory. You don't see a whole lot. Compton did not produce the pretty pictures that everybody wants to see. Yeah, bumped into that. There we go. So the Compton Observatory, being a gamma ray observatory, doesn't really coincide as well with some of the imagery that you're going to see. So what we have is we have Spitzer on one side, which is actually, it was, well, we'll talk about all of it. Hubble, this is the same galaxy, 101, M101, and Messier, Charles Messier was a comet hunter in the 1700s. His nickname was the Comet Ferret, and he created a list of 110 objects in the sky that were not comets and thus were not worth looking at. And we use his list of 110 objects today as some of the most interesting objects to look at in the nighttime sky. But so this is M101. It is a spiral galaxy, and so you get to see it in different wavelengths here. And so it just kind of gives you an idea, at least a little bit, that each of these different observatories gave us something different to look at and something different to study. And so they all have contributed to the scientific knowledge that we have today. So, let's see, M101 spiral, it's about twice the size of the Milky Way. Our Milky Way is 100,000 light years across, so this would be about 200,000 light years across. Spitzer infrared is showing the dust lanes very prominently. The dust in a spiral galaxy is where star formation is occurring. Hubble, of course, is the visible light. This is what we would actually be able to see. And then Chandra X-ray shows the high temperature, high energy areas. So basically, those are areas where stars have exploded, black holes are swallowing things, all sorts of different stuff like that. So the lack of the Compton gamma ray is just because really wasn't a whole lot to see. All right, so we'll start with Compton, since it got the short end of the stick for introduction. This is a picture of Compton as it was being deployed from the space shuttle Atlantis in April of 1991. It kind of almost looks just a little bit like a friendly robot, which in a lot of ways these observatories are. So, launched on April 5th, 1991. It was decommissioned June 4th, 2000. So it only lasted 9 years, but those 9 years were very productive. It studied gamma rays using 4 different instruments that looked at 4 different types of energy. It discovered a type of active galaxy called blazars. We have quasars, blazars, active galactic nuclei, all sorts of different things like that. So Compton actually discovered blazars. It mapped high energy areas of the Milky Way. To go a little bit deeper into that, it actually showed us some areas where aluminum was prominent in the Milky Way galaxy. And then Compton just hinted at the origins of gamma ray bursts. So what are active galactic nuclei? They're usually seen in galaxies very far away. Star Wars, essentially, which also means that we're looking very far back in time. The most active galactic nuclei are seen, basically beyond 6 billion light years. So these are galaxies that are at least 6 billion years old. To start with, there were all these different types of active galactic nuclei. Every different type, every different energy that we could see had its own name. But now, basically because of Compton and other studies, we now basically figure that all of these active galactic nuclei are very similar. It just depends on the orientation which that galaxy is to us and how we're seeing it, whether it appears as a blazar, a quasar, anything like that. So basically, it's all about the black hole. The giant black hole at the center of every galaxy, depending on how active it is, determines whether we're dealing with an active galactic nuclei. Our galaxy today, and they talk about this in the Supermassive Black Holes show, and some people get a little bit hung up on it. Our black hole at the center of our galaxy is considered dormant rather than active. That does not mean there's not material flowing into it, because there is, but it is not producing the same amounts of energy that these very, very young galaxies are. Gamma ray bursts, short, very intense bursts of gamma radiation. Originally, most scientists thought they came from our own galaxy, from interactions between neutron stars, but Compton showed that these bursts were actually coming from millions or billions of light years away for the most part. Now thought to be caused by the deaths of massive stars, and then the mergers of neutron stars or black holes. The mergers of neutron stars and black holes also lead to something called gravitational waves. Gravitational waves were first detected in 2014 or 2015 by the LIGO, Laser Interferometry Gravitational Wave Observatory. And we're actually getting to a point now, about 10 years after the first confirmed gravitational waves, where we can actually see the underlying ripples in space-time because they've been going on so long. So Compton helped us get going with all of that. Chandra is our next of the great observatories. The Chandra X-ray Observatory is the world's most powerful X-ray telescope. 8 times greater resolution, enabled to detect sources more than 20 times fainter than any previous X-ray telescope, and actually still just as good as any new X-ray telescope. Launched July 23rd, 1999. 25 years ago, still going strong, still active. As a matter of fact, if we, detects X-ray emissions from very hot regions. So this is one of Chandra's most recent discoveries. This image of the Helix Nebula, released March 4th, actually shows a white dwarf. So this is what our sun will look like eventually. About 5 billion years from now, plus a little bit, so that there's time for it to spread out. But this white dwarf probably at least partially destroyed a planet. And so the Chandra X-ray Observatory has been continually observing this for quite a long time. And they're just now starting to realize, okay, some of these X-rays may be coming from the interaction with the planet's destruction that's occurring. So it is definitely a very interesting thing. Not confirmed, but highly probable. And so, yes, this is what our sun will look like in 6 billion years, let's say. So, 5 billion years, we have to be off the planet, otherwise we're done. The way things are going right now, 5 years, we may have to be off the planet or we're done. Spitzer, Spitzer Space Telescope. This is an artist's conception of what it looks like out in space. It was launched on August 25th, 2003. The mission ended in 2020, just before the pandemic. It got lucky. Spitzer was an infrared telescope. Major discoveries included a ring of Saturn, the most remote galaxy ever detected up to that point, and the first known star system with 7 Earth-sized planets, which is TRAPPIST-1. This is just a nice little collage of some of Spitzer's most popular imagery. You have galaxies, nebulae, should be, that's a supernova, another nebula, another supernova, another nebula, another galaxy. So, but all of this is one of those things where the colors, and this is where we get into problem with some folks. If you were out there trying to look at these objects, you would not see these colors. The colors are added. The colors are added because they are added to simulate the wavelength at which we're looking. And so when you're looking at this, and granted, going back to infrared, we can't see infrared. So we kind of have to, make up some colors to let people actually see what's going on. But in some cases, if you were out there in space looking at these objects, you would see colors similar, but much fainter. our eyes just are not able to detect a lot of the energy that's actually coming from these, which is why we use these telescopes to actually help us out and be able to see some of these different energies that are out there. And then TRAPPIST-1, that's the big one from Spitzer, of course. TRAPPIST-1 has multiple planets, and if you start looking at them and everything like that, you can actually make guesses as to what those planets would look like. And so this is the artist's guess based off of the distance, the diameter, the mass, all of that from its host star. But all of these objects are actually more closely in size to the Earth than they are to the big gas giant planets like Jupiter, Saturn, Uranus, Neptune. And so there is possibilities based on where their orbits lie. There could be water on the surface of these planets. If there's water, there could be life. And so we have to go back and look at all of these things over and over, especially with things like James Webb, as we get better and better at what we can do. And eventually here, James Webb is going to start showing that there's oxygen around some of these objects. And if there's oxygen, there's almost guaranteed life, because oxygen does not stick around in areas where life does not replenish. And so all of the planets are made of rock. Some have up to 5% of their mass in water, and that's about 250 times more than the amount of water on Earth. So for all the water we have on Earth, it really doesn't make up a huge amount of our mass. So we're going to go beyond the great observatories. We'll talk about Hubble soon.
Andrew, might this be a good time for questions before the break? Or do you want to do a couple more slides?
Let me just talk about Kepler, and
Okay.
we'll talk about Kepler and James Webb real quick. And then we'll do the questions. So I'm trying to keep track here. Okay, yeah. So beyond the great observatories, Kepler. Let me pull that a little closer. This is an artist's concept of Kepler. Showing out there. It's actually showing Kepler in its second stage of usefulness, which was called K2. In 2013, the spacecraft lost its ability to maintain its orientation in space. It was looking at a very small section of space for its original portion of its science mission, and then ran out of the fuel necessary to keep it from drifting. So, but what they ended up doing then was they used the drift to their advantage and started looking at some other objects as well, and so that's why they call it K2, and they did find additional exoplanets. Launched March 6, 2009, officially fully retired in October 30th, 2018, with the at the end of its K2 portion. This telescope's sole mission was to look for exoplanets. It was designed to look for basically what we knew probably existed, but didn't really have a whole huge amount of luck finding before. There are more planets than stars. Our Milky Way, 200 billion to 300 billion stars. There could be 2,000 to 3,000 billion planets in the Milky Way. And it's almost a near certainty that it guaranteed that there's other planets out there that can actually support life, and that life probably exists outside of Earth. More than 2,600 exoplanets discovered by the transit method. Planets are everywhere is the quote that came out of Kepler. Kepler has opened our eyes to the diversity of planets that exist in our galaxy. Analysis of Kepler's discoveries concludes that 20 to 50% of the stars visible in the night sky are likely to have small, possibly rocky planets similar in size to Earth and located within the habitable zone of their parent stars. That means they're located at distances from their parent stars where liquid water might pool on the planet's surface. It's just nearly a certainty that there's life out there. And then the next one, this one's not up yet. Nancy Grace Roman Telescope. This is a picture of it being assembled at Goddard Space Flight Center. It'll be joined to its aircraft, to the spacecraft, and then launched into space. Hopefully, I say hopefully, I will say it again, hopefully, Nancy Grace Roman Telescope will be launched by May of 2027. We'll talk about it a little bit later, but Webb was just a little late. It will explore questions involving dark energy, exoplanets, and other areas of astrophysics. Named after NASA's first chief astronomer, the mother of the Hubble Space Telescope, Nancy Grace Roman Space Telescope will have a field of view at least 100 times larger than Hubble's, potentially measuring light from 1 billion galaxies in its lifetime. There are 2 trillion galaxies that we can see in the observable universe. And so they're going to try and measure light from 1 billion galaxies. This observatory will also be able to block starlight to directly see exoplanets and planet-forming disks, complete a statistical census of planetary systems in our galaxy, and settle essential questions in the areas of dark energy, exoplanets, and infrared astrophysics. Dark energy was known as the cosmological constant back when I did my PhD on it. It changed shortly thereafter, so I have to always remember dark energy and the cosmological constant are the same thing. So I was doing initial studies in dark energy with my advisor, and kind of makes me feel good.
An asteroid crashed into Mexico and destroyed a great deal of life on Earth, including the dinosaurs. What are the chances of something like that repeating itself?
Well, okay, so that asteroid 65 million years ago that basically wiped out the dinosaurs. Luckily, we haven't had anything quite that big since. The hope is that the biggest of those are kind of out of our way at this point, that we have been around long enough that some of those really, really big ones are less likely to cross our path. The possibility of it happening again is pretty good. But now I'm going to say, here's the thing. It's nothing that they are tracking at this point is actually anything that would come anywhere close to that. They have gotten so good at tracking asteroids that they are tracking asteroids that are 45 feet across. The Chicxulub crater was probably caused by an object that was at least 1,000 meters across, and probably closer to 2,000 meters across as it hit us at least. It's also possible that it split in half, and half hit that basically hit in the Gulf of Mexico, and half hit in like the North Sea area. And so that dual breaking could have actually made things even worse because of the way that things happened. Will it happen in the future? Maybe. But here's the other thing. We have already shown that we can successfully move an asteroid a little bit.
That big one? Like that big one?
Here's the thing. If it's that big, we can see it early. We will actually know it's coming earlier. And in order to move an asteroid that big, it doesn't take a lot of force. You just have to move it a little bit, and that'll change its course just enough that it might miss us. So the reality, if we're early and it's big, we can probably actually nudge it just a bit and then be good.
Blaine, any questions online?
Yes, we have three.
Well,
We have three, but one of them is a definition.
I was wondering,
Oh,
you keep referring to exoplanets.
yeah,
Is
right.
that different than a planet, or why the term?
The only difference between exoplanet and planet is who it's orbiting, or what it's orbiting. Exoplanets orbit around stars other than the sun. planets orbit around our sun, and that's the only difference. And there is no real good definition for a planet either, no matter what the International Astronomical Union says.
We have time for two more questions. One,
Yeah, we have-
Lane,
Let's-
you over here first, Linda, and then we'll go back. Nobody in Linda's section? All right, Blaine, you get 2 questions.
All right, here's a question for you, about night skies, less intrusive lighting. And, one of our, online people asked, I understand that Boulder City is in the process of changing its lighting to a more, dark sky, friendly, which seems like a positive step. Do you have any comments on that or suggestions for what citizens can do?
Oh, of course. The best thing you can do is to actually shield your light, so it's going downward rather than being sprayed out in all directions. When you shield your light and direct it where you want it to go, you can actually use dimmer lighting. You don't have to use as bright, and so that saves you money as well. And if you shield it so it's downward, you can use dimmer lighting, and then you tell people what you did, that you saved money by doing it. Other people will follow along. That's the one thing that a lot of people don't realize, is you can use less energy, less wattage, and have more light where you want it, and still make the skies darker than what we have. So that's the most important thing to take out of this, is advocate for dark sky lighting. Because if you can convince a company that all of their lights could be changed and it would cost them less money in the long run, then they'll probably be more willing to do it. Rather than just saying, ooh, we want the dark sky. They don't care.
Susan, I see Susie has a question up there, and you're gonna have to
Yeah.
have the break after that.
How much stuff is revolving around the Earth, like retired satellites and other junk up there?
Too many. NASA actively tracks 5,000 fairly large objects that are in orbit around us, and there are tens of thousands of smaller objects, bolts, nuts, pieces of debris, little tiny shards that of heat shields, and it's getting to a point where there's so much trash in orbit around the Earth that it's going to possibly make things difficult for launching new satellites. And so Japan especially, the JAXA, the Japanese Space Agency, is really working hard to try and develop methods to actually try and get rid of some of that stuff, but nobody has come up with a good way of doing it yet. It's a real problem, and it's going to get worse before it gets better.
Our break today is a little later than usual, and